Hi, this is Professor Fernandez, and this is video 3 in lesson 25. We're talking here about the increase and decrease of transcendental functions. There are a couple of examples that I'm going to run through. These come from Calculus Simplified. And because we're going to be using things like the increasing and decreasing test, you might want to review those. So that's covered in videos 13.4 and 13.5. Okay, so let's go ahead and take a look at these two examples, see what's here. The first one, example 4.13, says, find the intervals of increase and decrease for f of x equals, zoom in here, e to the 2x plus e to the minus x. Okay, so if you remember how this process goes, right, the first thing we have to do is find the derivative, and then we're going to set up a sign chart SIGN and look for where the derivative is negative or positive, and that will tell us increase or decrease intervals. So first step here, I'm going to find the derivative, f prime of x. Using some of my derivative rules here, the derivative of a sum is the sum of the derivative. So, and the first, actually both of these we're going to need the chain rule for. So e to the 2x, the derivative of that is e to the 2x times the derivative of what's up there, 2x, which is derivative of that is 2. And then plus e to the minus x, its derivative is e to the minus x again, times the derivative of negative x, which is negative 1. So that gives us a derivative of 2e to the 2x plus e to the minus x. There is no really right or wrong way to go about the next step. You could simplify, you could leave it as is, but really what we're looking for here are places where the derivative is 0 and the derivative does not exist. Those will give us kind of our candidate points that then we can look in between those points to look whether the derivative is positive or negative, and then conclude increasing or decreasing from the increasing or decreasing test. There is, you might, if you've seen some of those previous videos, like in lesson 13, I always do this part first where we're talking about are there any points where the derivative does not exist. There is a fraction here, so you might wonder or worry that there are x values that make the denominator 0. That would be an example of an x value where the derivative does not exist. But there are no such x values here because e to the x is never equal to 0. So we're only looking at where the derivative is equal to 0, and then this goes back to which one of these two forms are you going to use. So I'll just stick with this one. So I'm going to set this equal to 0 and then solve for x. So I can move over the e to the minus x, and then at this point I can multiply everything by e to the x. That's going to give me an e to the 3x here, and then e to the minus x times e to the x, that's e to the 0, which is 1. And then here I can divide by 2, and I can now, I now need to solve for x. I have to unexponentiate. That's what the logarithms do. The natural logarithm is the one to use here because that has the base e. So I'm going to take ln of both sides. And remember, ln of a to the b is b ln of a. That's one of our properties of logarithms we talked about in a previous video. So the 3x comes down. Remember also that ln of e is log base e of e, and that's just 1. So I don't have an ln of e here. That's just 1. And then on the right-hand side, I have ln of 1/2. So long story short, x equals ln of 1/2 divided by 3. You could leave it this way, or you could use yet another property of logs, right? Which is that ln of a quotient is the difference of the ln's. And you could then remember that ln of 1 is 0. So this becomes minus ln of 2. So we can rewrite x as minus ln of 2 over 3. You might be wondering which one of these is the preferred form, and it really depends on the context, right? For our purposes, we're setting up a sign chart. We'll do that in a minute. So we really do want to know whether this value is positive or negative. That will help us to pick test points that then we can plug back into f prime and tell us positive or negative. This is the one that helps us tell us positive or negative, right? So this is definitely a negative number. Okay, so then I'm going to set up my sign chart for f prime of x. I'm still, even though I'm now working under this example, I'm still doing this one because I'm running out of space here. And my sign chart tells me that the only point I have to consider here is minus ln of 2 over 3. So then I can insert candidate test points. So I'm going to choose an x value over here that's to the right of minus ln of 2 over 3. We can certainly choose 0. Again, provided that the function is defined there, and it is. The function is defined for all x. And then choosing a point to the left of this, well, we kind of have to know the actual approximation of ln of 2 over 3. So that ends up being about 0.23. So this is about negative 0.23. So I can just choose something like negative 1. And then what I'm going to do with that negative 1 here is that we're going to substitute it back into the derivative. So let me remove some of the clutter here. So we're going to stick with this version of the derivative. So let's try to see what happens when x equals negative 1. So what do we get? We get 2e to the minus 2 minus e to the negative 1. Okay, 2e to the minus 2 minus e to the first. So at this point, it might indeed help to have some sort of computational device, a calculator, or you can go on wolframalpha.com or something like that to approximate this quantity. Or another thing you might be able to rely on is this is 2 over e squared minus e. And e is about 2.71. You square it, it gets bigger. So this is like 2 divided by 9 or something like that, right? If we're rounding up for e. And then 2/9 minus about 3. So that's probably going to be a negative number. You can confirm that in fact it is using any one of those computational devices. So we have a negative region over which the derivative is negative. Okay, so go back, do this all over again. What if x is 0? So what do we get in that case? So let's substitute in x equals 0 in here. So we get 2e to the 2 times 0 minus e to the negative 0. So that's 2e to the 0 minus e to the 0. That's 2 minus 1, that's 1. So that was a lot easier to determine the sign SIGN for, so that's positive. Okay, so based off of this sign chart, what do we learn? Well, we learned that from negative infinity all the way up to minus ln of 2 over 3, the derivative is negative. So that tells us from the increase and decreasing test that the function is decreasing there, decreasing. So decreasing on. And then after negative ln of 2 over 3, from there off to infinity, the derivative is positive. So the function is increasing. So we would say increasing on that interval. And that's basically, we answered the question, right? Find the intervals of increase and decrease for f of x. One thing to mention here, and I will do that while I'm erasing all this other stuff, is that how come it goes all the way out to negative infinity and all the way out to infinity, right? How did I know that those were the quote-unquote endpoints of my interval? Well, one thing to do is always think about the domain of the function. So in this case, the domain of f of x is minus infinity to infinity. We know that because, again, writing this as e to the 2x plus 1 over e to the x, we could, if we wanted to, find a common denominator and write the function this way. You can see that the denominator is never 0, right? There's no x value for which e to the x equals 0. And then the numerator is defined for all x, as is the denominator. So this function's domain is all real numbers. So that's why we get to go all the way out here and all the way out here when determining our intervals for increase and decrease. Okay, so let's take a look at the second example down here. Part of the reason why I just mentioned all that information about the endpoints in the domain is that in this example, it's a different story. So let's take a look over here. So this one says, let f of x equal 2 cosine x plus cosine squared, where x equals, or x is between 0 and 2 pi. So this is a much smaller domain that we are asked to consider. So that's why it says find the subintervals of increase and decrease. Okay, so I am going to make use of all the space that is here. That's why we wanted to erase everything. So I'll actually start up here. We'll start in the same way. We'll find the derivative of this function. So derivative of cosine is negative sine. And then cosine squared, remember, cosine squared x is cosine of x squared. So to differentiate this function, I need to apply the chain rule to that. So derivative of the outside, evaluate at the inside, times the derivative of the inside. The derivative of cosine is negative sine. Okay, so that's my derivative. Let me simplify it a little bit. Both of these have a minus sign, x, and both of these have a 2. So let's factor that out. And what am I left with in the first term? That's the entire term, so 1. In the second term, I'm left with this part here, so plus cosine x. Okay, so now I have my derivative, and I will then go off and do the same analysis. Are there any points where this is equal to 0 or does not exist? Like we did before, we answer this question first. Sine and cosine are defined for all real numbers, so again, that's another domain question there. So there are no points where this particular combination of sine and cosine is undefined. So none of these. Okay, and then we're looking for where it's equal to 0. So let's set them equal to 0 and then see what happens. So if I set this equal to 0, I have two possibilities. So either sine x equals 0 or 1 plus cosine x equals 0. Okay, so I have two equations to solve here. Cosine x equals negative 1. And sine x equals 0. So those are the two ones that I'm going to talk about in a minute. Excuse me. So for solving these two equations, right, you have a few options. Some of the ones that I've kind of mentioned, you can go to Wolfram Alpha, you can have it do that. You could graph the function. You could remember the table of values for sine and cosine. So lots of options. What I'm going to do here is first remind you that we only want to, are interested in the values of x between 0 and 2 pi. So if we look at the graph of sine, for example, it looks like that, between 0 and 2 pi. And this is pi. So if we're looking for where sine is 0, right, that's here, here, and here. So this is going to tell me that x equals 0, pi, and 2 pi. Okay, great. So what about the other equation here? How about cosine of x is negative 1? Well, let's graph cosine of x. From x equals 0 to 2 pi, so that looks like that. This is 1, this is negative 1, and then this over here is pi over 2, this is pi, oops, just pi, and then this all the way out here is 2 pi. Okay, so, again, these are sketches, this is not the actual graph, but we're looking for where cosine is negative 1. So, right over here, in my pseudo graph, more like a sketch, is the x value between 0 and 2 pi, where cosine of x is equal to negative 1. So x equals pi. All right, so from these sets of numbers, pi is already included in here, and we also have 0 and 2 pi. So really, this is the information that we're going to use to then construct our sine chart. So I'm going to do that over here. So let's look at a sine chart for the derivative f prime of x. And we're looking at, I'm going to put here on the left-hand side, the left boundary of the interval, 0. On the right-hand side, the right boundary, 2 pi. Okay, and then I'm going to put all the other points that we want to, that we got from here. So we got 0, we got 2 pi, and then we got half of it, we got pi. And you can see really that there are only two intervals that this splits up our original 0 to 2 pi interval into, not more than that. Because two of these points, 0 and 2 pi, are the endpoints of the interval. So, we're not going to consider x values over here. We're not going to consider x values over here because that is outside our interval. So, really, all we have to do is consider x values in these two subintervals. And as usual, you can pick whatever values you want, but it would be nice if you picked values that you know sine and cosine values for. So something in between 0 and pi that we know sine cosine values for example, is pi over 2. And then similar for over here, 3 pi over 2. Great, so I'm going to pick those two x values, substitute them into the derivative, which is up here, and then see if the sign SIGN is positive or negative. Okay, so sine of pi over 2, well, sine of pi over 2 is 1, so that would give me 1. Cosine of pi over 2 is 0, so I would get negative 2 times 1 times 1, in other words, a negative. So negative number. Okay, go back and do that over again. How about sine of 3 pi over 2? So sine of 3 pi over 2, that is all the way at the bottom of the xy axis, right? So 3 pi over 2 goes all the way over here. And sine is the y value on the unit circle, so that would be equal to -1. So that would be, this would be negative. This is negative. Cosine of 3 pi over 2, that is the x value on the unit circle. X is 0 here, so that's 0. So I get negative times 1, so negative negative equals positive. So positive over here. Okay, so we've drawn a sine chart, and now we can go back and see step back and see what it tells us. So what does it tell us? It tells us that the function is decreasing before pi and then increasing after pi. And again, we're stopping at 0 and 2 pi. So I would say, where is it increasing? From pi to 2 pi. Great. And then where is it decreasing? From 0 to pi. Oops, there we go, 0 to pi.